Continuing with section 2.3, we now look at example 3, which says, let A and B be n by n matrices. So it means A and B are square matrices. Show that if A times B is invertible, so is B. A times B is invertible means there exists an n by n matrix, whatever we can call it, and such that that matrix times AB is going to give us an identity matrix, and that's what we will need to show for the B. So AB is invertible. Well, what it means is that which implies there exists an n by n matrix, let's call it W, such that W times AB is equal to I. Okay, so we need to put parentheses around AB because that is together, and then we have the W being applied on the left. And now if you recall, there is a property of matrices. I can move the bracket, so this implies, or this gives me bracket or parentheses WA parentheses close times B equals I. So I move the parentheses on WA, so B is kind of now alone. So now we see it as B times a matrix is equal to I. So which means B is invertible. So this implies B is invertible. And in a similar way, you can show that A is invertible. But that was not asked here, so we'll just stop and look at the next example, example 4, which is saying, let T from R2 to R2 be linear transformation as defined below. Show that T is invertible and find T inverse. So if you recall, with every transformation, there is a standard matrix, and the matrices for the coefficients of these vectors, or you can get the A by using the standard vectors, base vectors. So E1 is equal to, in R2, E1 is equal to the vector I, the vector 1, 0, and E2 is equal to 0, 1. Okay, so if we do T of E1 will give us parentheses 2x1, well x1 is 1, so we get 2, minus 8x2, x2 is 0, so we say that we are in the first place we have just 2 and then comma. Now the second coordinate, so we have negative 2x1. Now x1 is 1, so we get negative 2, and plus 7x2, x2 is 0 for E1, so this is the first image of the transform. So then T of E2, so this is giving us the vector 2, negative 2, which will be the first column of A, and we do the same thing to T to E2, which is giving us so doing it the same way. The first one gave us negative 8 because in E2 the x1 is 0 and x2 is 1, so we are getting negative 8 comma 7, which is the vector negative 8, 7. So the A matrix here is so it will be the 2 by 2 matrix with the first column as 2, negative 2, and the second column as negative 8, 7. You can see that determinant of A is 14 minus 16, which is negative 2, which is not equal to 0. So which means A is invertible, but then that means T is invertible, and so now we need to find the A inverse. So remember, A inverse is equal to, so 1 over the determinant, so 1 over negative 2 times, and we change the position of 2 and 7. So in place of 2 we will get 7, and in place of 7 we will have 2. So 7 and 2 here, and with the 8 and negative 2 we will change their signs. So we get 8 and we get 2 here. Now I can even multiply the negative 1/2 inside. So we get all the quantities are negative now, and this one is negative 7 over 2, negative 4, negative 1, negative 1. So this is A inverse, so that your T inverse will be so the T inverse of x1 comma x2 is equal to Okay, parentheses, and remember we are going to read it from top to bottom, like up to down. So the first column gives us the coefficients of the x1 and x2. So it will have negative 7 over 2x1 minus x2 comma. So second coordinate will be negative 4x1 minus x2. So that is the inverse transform.